Okay, welcome back. So last time we discussed the units in the ring of integer of the quadratic field OD, and we showed that if D is negative, then there are only finitely many units. And so first criteria we used in general for any D, whether D is positive or negative, whether D is 2 mod 4 or 3 mod 4 or 1 mod 4, that uh, x square plus dy square. Uh, so x square. So the element, an element is a unit if and only if it has norm one. Okay, and so for negative integers, the norm one elements are only finite, and they're in fact only plus and minus one. If unless d is equal to minus 1 or d is equal to minus 3, in this case d minus 1 zi, then 4 units plus minus 1 plus minus iota, where iota is the square root of minus 1. And the other case where d is minus 3, there are 6 units plus minus 1 plus minus omega and plus minus omega square, and omega is a primitive cube root of unity is equal to minus 1 plus root minus 3 by 2. Now coming to the real case, we showed that there are certain units, namely solution of x, y, and z, such that x square minus dy square equal to 1. So, I said it somewhere. Yeah, so this equation, x square minus dy square equal to 1. And so in norm, for d equal to 2 or 3 mod case, you can see that they gives you units, and we'll show this equation has, this is called Brahmagupta equation or Brahmagupta-Pell's equation, as x square minus dy square equal to 1 has infinitely many solutions. Okay, so these are not all the units, but we'll show that this equation has infinitely many solutions, and this will give you infinitely many units. On the other hand, even in 1 mod 4 case, we'll continue to study the x square minus dy square equal to 1 and show it as infinitely many solution. So then again, they will give us infinitely many units. And so the conclusion was this: for infinitely many integer solution of this x square minus dy square equal to 1, which we will show, we get infinitely many units in OD for any d greater than 1, both in these 2 or 3 mod case or 1 mod 4. Then we show some example that in Z root 2, we'll show that all the units are 1 plus, at least the positive units are, so at least we'll show that x square minus 2y square equal to 1, all the solutions are given by 3 plus 2 root 2 to the power n, where n is z. And from there, it's not hard to see that x square, all the units are given by, in fact, plus minus 1 times 1 plus root 2 to the power n, where n is in z. Okay. And I gave another example that d equal to what is happening in d1 mod 4 case. So for example, root 5 plus 1 by 2, I called it alpha. This is a unit. This is not in z root 5. So, and its norm is minus 1, and it's a unit. But if you take its sixth power, it's a solution of x square minus 5y square equal to 1, which is 9 plus 4 root 5. And it is a fundamental solution of this equation x square minus 5y square equal to 1, in the sense you can generate all other solutions from this solution. Okay, so I'll not prove it, but I'll give you a hint how to discuss this. Okay, and in fact, if you take its cube, then you get this 2 plus root 5, which is a solution of x square minus 5y square. So, okay. So anyhow, so we'll focus on, for all cases, x square minus dy square equal to 1 on the solution of that. And somehow I'll state a theorem from where it will be clear that there is not much difference from the general case, all units. Okay. So there is this, so what was Brahmagupta's idea? Okay, so Brahmagupta's idea. Suppose, so again, you take d greater than 1 square free, d is in z, and let's just write it this way: square free, d is in z, and so this doesn't look like a square, maybe something like this. So, and you have x square minus dy square equal to 1. If a plus b root t, so if ab, So if AB belongs to Z and ST belongs to Z, satisfy x square minus dy square equal to 1, then you get a plus b root d into a minus b root d equal to 1, and you get c plus, sorry, s plus t root d into s minus t root d equal to 1. So if you multiply this here, you get a plus b root t into s plus t root t into a minus b root t into s minus t root t equal to 1. So this is just taking product of this two solutions. So this gives you as plus b td plus at plus ps into root t, right? And similarly, as plus btd minus at at minus at plus bs into root t. This is equal. This implies that as plus btd and at plus bs, this tuple is a solution of x square minus dy square into 1. So given two solutions, A, B, and ST Z square, you can get new solution AS plus BTD, AT plus PS, Z square of C square minus dy square. In particular, if AB is a solution, then a plus b root t to the power n, right? You take square, you take cube. This gives infinitely many solutions. So let's say AB is an n square. Okay? Let's take a positive solution, that AB non-trivial solution. So for example, x is 1 and d equal to 0 is always a solution. Or x is minus 1, d is equal to 0 is a solution. So if there is a non-trivial solution, so if there is a negative solution, then you can change x to minus x and y to minus y. That will also be a solution. So this, right? So just composing them like this. Okay, so you understand what I mean by here. So you take s equal to t, then like a squared plus b squared t, and then so sorry b squared t is equal to, so you put here, for example, here s equal to a and here t equal to b, then you get so you can see that, square of that will give you a solution like a square plus, so this will be a square plus, for example, b squared d, and here it will be a b plus 2ab will give you another solution, right? So for example, if 3 plus 2 root 2 is a solution, then so if 3 2 is a solution of x square minus 2y squared equal to 1, then you'll get 9 plus 4 into minus 2, and sorry, 4 into 2, and 2 into 3 into 2. So this is 17 and 12. So you know 17 square minus 2 into 12 square is equal to 1. Okay, 289 minus 288 is equal to 1. So once you get 3 and 2, so 3 plus 2 root 2 is a solution, then you take the power, then you get 17 and 12 is a solution, and continuing like that. And you get infinitely many solutions. So, yeah. So, so 3 and 2, which corresponds to, maybe I can write here 3 plus 2 root 2 for x square minus 2y square equal to 1. Then 3, 2 into 3, 2. This corresponds to 17, 12 is another solution. And you note that a plus b root d, if a is positive and b is positive, so then both are greater or equal to 1, then this is greater than 1. Okay, so a plus b root d to the power n, these are all distinct. So if you get one norm one element, then 3 plus 2 root 2 to the power n, this will all be, they'll never be equal. Okay, and also norm of 1 by x is equal to norm of, so is 1 by norm of x. 1 by norm. So if 3 plus root 2 is a solution, then 1 by 3 plus 2 root 2 will also be norm 1 element, right? So that's why you get here, we said that norm 1 element will be given by 3 plus 2 root 2 to the power n belongs to 0 for x square minus 2y square. Okay. So that's how we'll generate more solutions. So this was Brahmagupta's idea that given two solutions, you can keep it also. So given two solutions, we can generate more solutions of the Brahmagupta-Bell's equation. If we have two solutions, then whatever this means, this dot, we can generate more solution, and that way we can get infinitely many solution. Okay. So we'll formally prove this, but this was the idea that so given two solutions, you can get another solution. This is clear using the norm of xy is norm x into norm y, and if x is norm 1 and y is norm 1, the norm of xy is also 1, and norm of 1 by x equal to 1 by norm of x. So if 3 plus 2 root 2 is a solution, then 3 plus 2 root 2 square will also be a unit, and 3 2 is a solution, then corresponding to 3 plus 2 root 2 to the power n, you will get infinitely many solutions. And even 1 by, so if n is in z, those will also correspond to solution. Right? So that's how this thing works. And in fact, the most general result is in this direction is called Dirichlet's unit theorem, which says if d is this will not prove positive square for integer, then there exists one unit such that every unit can be written as integer power of that unit. So plus minus 1 times z. So example is you have 4 2 star is equal to plus minus. Yeah, so we have already written here in this example that there is one unit that every other unit can be written as some integer power of. So here it is 1 plus root 2. And so Dirichlet's unit theorem says for any quadratic field, this is the case, that there exists one single unit, and that all other units are plus minus 1 times power of that unit. And so we are not doing much worse. So but this 1 plus root 2, this has this corresponds to x square minus 2y square equal to minus 1. But it's squared, which is 3 plus 2 root 2. So this guy corresponds to this. This corresponds to x square minus 2y square equal to 1. Okay, so we are capturing all even powers of this, which is not too bad if you think of it. Okay, so this is a general theorem which will not prove. that always for any quadratic field there is a single unit, so that all other units can be uh, can be taken to be a power of that unit. Okay. Okay. So this is called Dirichlet's theorem, but we will not prove this. So let us now go back and we want to prove formally that we want to see this statement. First, we want to prove this statement that in O2 star, every element looks like, every unit looks like this. And yeah, so yeah, every element looks like 3 plus 2 root 2 to the power n in z. This will be okay. So let us put it in a slightly more general context. So a positive integer is said to be a triangular number if it is can be arranged in the shape of a triangle. So for example, 1 is a triangular number and 3 is a triangular number because it can be arranged like this. Then 1 plus 2 plus 3, which is 6, is a triangular number. Then next is 1 plus 2 plus 3 plus 4. This can be arranged in shape of a triangle. So the nth triangular number is sum of 1 to up to m, which is m into m plus 1 by 2. And simply a positive number is called a square number if it can be arranged in the shape of a square. So for example, 1 is a square number, 4 is a square number, 9 is a square number, right? So the number of numbers, integers, which are also square number as well as a triangular number. So that will happen if n square equal to m into m plus 1 by 2 for some m. So if you clear this, you get, so if you multiply by 4, 8 on both sides, you get 8n square equal to 4m square plus m. So 2m plus 1 whole square. And if you set x equal to 2m plus 1 and y equal to 2n, then you get this equation x square minus 2y square equal to 1, which is a Brahma-Gupta-Briggs equation. And if you solve this equation, you get an xy an integer. Then you set m equal to x minus 1 by 2 uh, and y equal to n equal to 1 by 2. Okay, so so you know here x has to m this x has to be odd because this is even and this is odd, so this odd x is odd and yeah, so x minus 1 by y by 2 makes sense, and you can check that then y has to be even, and looking at like uh, mod 4, so this also makes sense. So by observation, you see that 3, 2 is a solution, which gives the square triangular number with mn equal to 1, 1. Another is 17, 12. So, and we checked that how from 3 to 17, 12. So basically to check when 1 plus, if you bring it to this side, when 1 plus 2y square is a square, right? It's a square. So for example, y equal to 1 to 3, you check when this becomes a square. So when y is 1, then you get 3, so it doesn't work, and you put y equal to 2, then you immediately get that this is a 9. So it works. And if you put like that, y equal to 12, then you get 17, and so on. So what is the complete solution? So again, what you are looking at is 1 equal to x square minus 2y square, which is we can be written as x plus root 2y, x minus root 2y, and xy will looking at z cross z. And in fact, once I find a solution, minus x minus y is also a solution, so I can take xy to be positive. So anyhow, so then you get 1 square. So this thing we did, if you find you find one solution, then you compose them to get two solutions. So if A, B, and C, D are two solutions. So here, for example, x plus root 2, xy is a solution, then you take x plus root 2y square into x minus root 2y square. This is 1 square. This I explained before. So you get x square plus dy square, and there I wrote a square plus 2 x square plus dv square and 2ab. So this is also a solution, and this can be again written as c plus 2 root d into c minus 2 root d. So, and as I said, 3, 2 gives you 17 and 2 square. So, and I have explained to you this way that if you have two solution A, B, and C, D, then you 1 equal to A plus B root 2 and A minus B root 2 because A square minus 2B square is 1, and same for CD. Then you multiply them and then you get AC plus 2BD, AD plus. So it is AC plus 2BD and AD plus BC into root 2. And similarly AC plus 2BD again and AD plus minus AD plus BC into root 2. So like that, two solution gives another solution. So if you have 3 plus 2 root 2 is a solution, then 1712 will be a solution. Then you multiply 1712 again, 3, 2, then you get 3 2 plus 2 root 2 to the power k, and infinitely many solution of this. And if 3 plus 2 root 2 is greater than 1, so 3 plus 2 root 2 to the power k is never equal to 3 plus 2 root 2 to the power n, for if k and n are distinct. So you get infinitely many solutions this way, for sure. So you get infinitely many units in z root 2. And yeah, so for the next part, we are largely following the expression of Keith Conrad for this. So just acknowledging that. However, any inaccuracies will be mine and not him. Hopefully, there are not many. So, square triangular number theorem. So, xy belongs to n cross n, x square minus 2y square equal to 1. And then all such xy is given by if you write xy. So, all the solutions are coming from 3 plus 2 root 2. So, if you raise 3 plus 2 root 2 to the power k and you write xk plus yk into root 2, then that's your all the solution of this. There are no other solution. Okay. So we produced a bunch of solution from 3 plus 2 root 2 to the power k, and claiming these are all the solutions. So first you note that if you have two solutions, x1, y1, and x2, y2, two different solutions, then their x coordinate cannot be seen. Because if x square minus 2y square equal to 1, and if x1 square minus 2y1 square equal to 1, and if x2 square, sorry, excuse me, x2 square minus 2y2 square is equal to 1 as well, uh, uh, then x1 is not equal to x2 and y1 is not equal to y2. So both the solutions are very different. That's what we are saying. And that is because if x1 equal to x2, then 2 into y1 minus y2 square equal to 0. That means y1 equal to plus minus y2. But since they're natural number, y1 has to be equal to 1, because otherwise one of them will be negative. We are restricting to positive integer solutions. Okay, so we are restricting to positive integer solutions. And as I said, if you find x, y, and solution, then looking at minus x and or minus y, you can always find a positive integer solution. So without loss of generality, we can do that. And we are excluding 1, 0 solutions. So we are looking at non-trivial solutions. Okay. So 1, 0 is 3 plus 2 root 2 to the power 0, for example. Okay. So similarly, if two coordinates as y1 and y2 equal to same, then x1 square has to be equal to x2 square, and then x1 has to be x2. Okay, so also further you look at first coordinate cannot be 1. If x equal to 1, then you get 2y1 square equal to 0, so y1 equal to 0. That's the trivial solution. So 1y, where y is in n, and 2z. Similarly, if you put x equal to 2, then you get 4. So 2y 1 square equal to 3. So there is no solution to that. So 1y and 2z, y and z in n never satisfy this. Okay, equation this. And if you put x equal to 3, then you get 9 minus 1. So 2y1 square equal to 8. So y1 square equal to 4. So y1 has to be equal to 2. It can be minus 2, but we are looking at natural numbers. So in some sense, this is the smallest solution. So this is the smallest solution in this sense that this is a solution in natural number with the smallest x coordinate. And later we'll see this is the general case. If you find a solution with x, y are in positive integers and x, the one of the coordinate, like x coordinate is the smallest, then all other solutions looks like that solution form. Okay. So we claim that if UP belongs to a natural number and satisfies u square minus 2v square and greater than equal to 1 with u greater than 3, then it has to be equal to uh, 3 plus 2 root 2 into s plus p root 2 first, and where st are in n and s is less than equal to u. Okay, first we'll prove this. Okay. So to prove this, this is easy actually. So you want to solve that. This is always solvable because, so for 1, not from 1. So for 1, u plus, so then what is u plus v root 2? You just expand this, right? So you just expand this. This is 3s plus 4t plus 2s plus 3t into root 2. So to prove, maybe I should just highlight this is the same. And similarly, this. So to prove this one, we have to solve that. Then u equal to 3s plus 4t and v equal to 2s plus 3t. That means s has to be 3v minus 3u minus 4v. It's a linear equation. So the solution is s 3v minus 3u minus 4v, and t is minus 2u plus 3v. So you wanted to find s and t. I'm telling you what is s. You define s to be equal to this, and you define t to be this, and then you do the back calculation. And then, of course, it satisfies this, but st is also a solution. Okay, s square minus 2t square is 3u minus 4v square minus 2 into minus 2u plus 3v square, and that you calculate that answer to be square minus 2v square equal to 1. So st is another solution. Also, u square is 1 plus 2v square is greater than 2v square. So then s is 3u minus 4v, and then u and v are all positive. So u is greater than root 2v. So you put it here, and minus 4v. So 3 root v minus 4v. So s is positive. Okay. And recall this was the assumption that u is greater than 3. So u square plus 8u square, 9u square. So u is greater than 3, so u square is greater than 9, and u square plus 8u square is greater than 9 plus 8u square. That means you bring it here, 8u square minus 1, which is 2v square, is greater than, so 9 into, if you like, u square minus 1, right, is greater than 8u square, right? So you bring here, how should I say this? So u square minus 1, so 9u square minus 9, I want to say 9u square. Yeah, so this is 9u square minus 9 is greater than 8u square. So that's what I have written. U square minus 1 is greater than 8 by 9u square, but u square minus 1 is 2v square. So 2v square is greater than 8 by 9. So 2 you cancel. So v is greater than 2 by 3u because we are dealing with positive things. So that's t. So s is positive and t is also minus 2u plus 3v. So minus 2u plus 3 into v is 2 by greater than 2 by 3u. So 2 by 3u. So this is positive, right? This is 2u plus minus 2u plus 2u. So this is 0, but this is a strict inequality. This is equal to 0. So t is strictly greater than 0. And u, which is 3s plus 4t, and t is greater than 0. So 3s plus 4t is greater than 3s, which is greater than s, as s and t are positive. So we got, so there exists s and t, and s and t and s square minus, and also here I can add s square minus 2t square equal to 1. Okay? 2t square. So all these things are satisfied. Okay, so so if s equal to 3 and t, so so s is less than u. Yeah, so u v. Okay, so u, if u and v satisfied So if there is a solution in natural number u and v where u is greater than 3, then we are managed to write it as 3 plus 2 root 2 into s plus t root 2, where s and t is also a solution, and st are positive integer, and s is less than u. So s is less than, and u is greater than 3. So s is less than u. So if s is 3, then t has to be equal to 2, and u plus v root 2 is 3 plus 2 root 2 square. If not, then s is greater than 3, right? So then you write again s plus t root 2, we can do this, p plus q root 2 with pq greater than 0. So whatever happened in 1, with pq belongs to n, and p is less than s now, and p square minus 2t square equal to 1, and I should add t square minus 2t square equal to 1. Okay, this is also there. So then you get u. So then again you can apply 1 to you get 3 plus 2 into p plus n. And then your u plus, so your u plus v root 2 becomes 3 plus 2 root 2 square into s into p plus q root 2, right? So this cannot go on indefinitely, because you are getting s, u is greater than s, and s is strictly greater than p, and then all of them are greater or equal to 3. Forms a decreasing sequence of natural numbers. It will, at some point it has to hit 3. So this cannot have infinitely many distinct numbers by Euler-Lorentz principle. So this process will stop at finitely many steps and will hit 3. And u plus v root 2 will be equal to 3 plus 2 root 2 to the power k. Because if, so if s is strictly greater than 3, then I can always produce a p which is strictly greater than s. So then that p will be equal to 3. If that p is also not 3, then I can produce something strictly smaller than 3. And then again, I get this factorization, right? So it has to stop at some point, and we get k is equal to n. Okay. So this is the proof. So we showed that every solution looks like 3 plus 2 root 2 to the power k. So in some case, we did the n equal to 2 case. So x square minus 2y square equal to 1. All the solutions are given by 3 plus 2 root 2 to the power k, where k is in n positive solutions. And then, as I said, if 3 plus 2 root 2 is the solution, then 1 by 3 plus 2 root 2 will also be a norm 1 element. So all the norm 1 element will be given by 3 plus 2 root 2 to the power n, where n is in z. And in fact, you can add norm minus 1 elements also. So this group is isomorphic to z. So this group is cyclic, and this group is isomorphic to z. Okay. The unit is plus minus 1 times z, as predicted by Dirichlet's integral. So generally, if you want to take norm minus 1, so you have z root 2 star is isomorphic to plus minus 1 times 1 plus root 2 to the power z, and you can to the power n, right? So to the power n, where n belongs to n. N, where n belongs to z. This will give you all the solution of, but plus minus 1. But so this group is isomorphic to. So you can finally prove O is O2 star isomorphic to plus minus 1. So Z mod 2Z direct sum set. Okay, this is what you can show. And generally you have OD star, and but we did norm 1 element. Norm 1 element forms a subgroup, and that will be isomorphic to 3 plus 2 root 2 to the power z. Okay. Yeah. Okay. So now for the general case, now we want to consider the general case. So Brahmagupta. So the main idea remains the same, that if you have two solutions, then a plus b root d and a plus b root d, then you compose them, namely you multiply them, a plus b root d into uh, s plus t root d, then that gives you another solution of this equation. In particular, if you find a solution that is greater than 1, like 3 plus 2 root 2, then its power k gives you all the solution in positive integer of x square minus 2y square. Okay. And so for the general case, we need to prove this thing, which is called now we want to discuss Brahmagupta-Pell's equation integer solution for the general D. Okay, so this is for a general D. In color d greater than 0, d square free, and we want to discuss x square minus dy square equal to 1. And as I said, this gives you norm 1 solutions of this equation. So it gives those units which are norm 1, and it corresponds to those elements in the ring of integer which has norm 1. Yeah, so to do this general case, first we need to discuss. So by the way, in this 2 case, I did not prove that all the things are given by root 2 plus 1 to the power n. I only discuss norm 1 elements, what happens to norm minus 1. So you can work it out. Okay? So Dirichlet approximation theorem. So you take d. So for the general solution of the Pell's equation, x square minus dy square equal to 1, which will correspond to norm 1 element in the ring of integers. We need this Dirichlet approximation theorem. So let's d is not equal to 1. D in z be a square free integer. And then there are infinitely many x comma y, x comma y in plus n, x comma y n. I can choose x, y co-prime to each other such that x minus y minus root d is less than mod of 1 by y square. So one also sometimes like state this as over z, but you can actually choose it over n. Doesn't matter. So what it says is irrational number, since d is square, free root d is an irrational number. So this irrational number can be very closely approximated by rational numbers, x by y. And this approximation is very close because, there are infinitely many y, so and 1 by y square will tend to quite small, and you can choose this way so that, so there's a close approximation. And there are many such approximation theorems. And always when you approximate a rational number by rational number, you get. So more generally, you can do it for any rational number. Actually, root d is not important. You maybe need to adjust something, but there is a general version also. And there are stronger theorems. There are many approximation theorems, but this one suffices for us. So we'll just consider this. And proof is particularly simple. Proof is actually by what is called pigeonhole principle. So for any natural number, so in fact, to prove this Dirichlet's Brahmagupta's equation, we'll apply pigeonhole principle many times. Okay? This is the first application in this form of Dirichlet's approximation theorem. So for any natural number n, you consider this interval 0 and open 1, and you divide it into n intervals, 0, 1 by n. N is any natural number, then 1 by n to 2 by n. And left side is closed, so you are including 1 by n the second interval, but not including 2 by n, all the way up to n minus 1 by n and 1. Then for any alpha in R, box alpha denotes the largest integer less equal to alpha. And this curly bracket alpha denotes the alpha minus box alpha. So if it is 1.5, box alpha is 1, and this curly alpha is 0.5. And if alpha is 0.5, then box alpha is 0, and or it is 0.1. If alpha is 0.1, then box alpha is 0, and curly alpha is 0.1. Okay, and so alpha lies between 0 and it can never be 1. So there are then n plus 1 numbers, 0 root d, 2 root d, n times root d. The curly bracket of that. If somehow m times root d curly bracket becomes n times root d, then that will mean m alpha minus box of m alpha which is an integer equal to n alpha minus box of n alpha, and that will make alpha to be a rational number. So that is not the case because root d is irrational. So this will be n plus 1 distinct numbers. And how many intervals we have made? We have made n intervals, 1 by n, 2 by n by n. So at least two of them will lie in the same interval, length 1 by n, right? So then there exists integer j and k with j greater than k, such that j root d, this one, minus k root d is strictly less than 1 by n. Okay? They're in the same interval, so their difference must be strictly less than 1 by n. That is x minus y root d is less than 1 by n, where y is j minus k, and x is box of k root d minus box of j root d, right? So greatest integer function. Now note that y is positive, 0 less than y less than n. So that means x by y, I can divide now. So I have x with x equal to this, k root d minus j root d. So I can divide it by y, which is j minus k. Yeah, j is greater than k, j minus k, and j is upper bounded by n. So so this is less than this was less than 1 by n, and this is less than this is less than this is less than 1 by ny, and this is because we are dividing by 1, this was less than 1 by n, and this is less than equal to 1 by y square, right? Because so ultimately you get x minus y by root d is less equal to strictly less than 1 by y square. Also, you see x, so you have x minus y root d is strictly less than 1 by n. So if you remove the modulus, so minus 1 by n is strictly less than x minus y by d. So x is greater than y root d minus 1 by n. So, but y is greater or equal to 1, so y root d is greater than root d, and 1 by n is less than 1, less equal to 1, and y is greater or equal to 1. So minus 1 by n is greater than minus 1. So this is strictly greater than root d minus 1, positive. So x can be chosen to be positive. So we may assume x is positive, y is positive, and then we can take, because then in this form, we can take GCD of xy to be equal to 1. So whatever common factor is there, you can remove. So we got 1 x by y such that x by y minus root d is less than 1 by y square. But we want infinitely many. So to obtain infinitely many solutions, to infinitely many not solutions, an inequality such x by y. Note that mod of x by y minus root d is never 0 because root d is rational, this is rational, so this can never be 0, otherwise root d is become rational. So module this is positive, and choose a positive integer m naught greater than 1 by this modulus. So presumably this is small and 1 by this is big, which is an even bigger integer. So by repeating the same process, n with m naught, we get x1 y1 instead of x1 y1 instead of xy, such that 0 less than y1 less than m naught, and you can take y is equal to m naught, let's say, and x1 minus y1 by root d is strictly less than 1 by m naught into y1, and that is strictly less than equal to 1 by y square. And further, x by y1 minus root d is strictly less than. So this is just same thing. Instead of n, you apply m naught, you get your x1 y1. And so we can. So this x1 y1, how is it distinct? How do you know it is not the same x0 y1? That is because x1 y1 minus root d is less than 1 by m naught times y1 is less equal to 1 by m naught. I can write because this is 1 by y1 is less equal to 1. So I can say this is less than 1 by y0. So this is strictly less than x by y minus root d, right? So x1 y1 minus root d is strictly less than x by y minus root d. So x1 by y1 cannot be equal to x by y. So I started with xy, then I found another x1 y1 which also satisfies this. Then you again take m double naught equal to 1 by greater than 1 by mod of x1 y1 minus root d. So you can continue this way And you get infinitely many x by y into q such that this is less than 1 by y squared. Further, we can choose x, y in n and GCD of each stage x, y. So we'll see how it is useful to us next time. Thank you.